Okay, so yeah, it's a great opportunity to give this talk. I really appreciate the invitation. So where I'm coming from, so I work here at QUICS, which is the Joint Center for Quantum Information and Computer Science at the University of Maryland in the U.S. And I also work at the National Institute of Standards and Technology, which is about 35 minutes away from here. And one of the main topics of interest in both places is post-quantum cryptography, and that is going to be the topic of this talk today. So what this is basically sort of a historical tour about everything that was leading up to and including post-quantum cryptography. And then at the end, I was going to give a little bit of technical stuff about the mathematical underpinnings in this topic. Okay, so I'll go ahead and start. So when I was growing up, I grew up around here, and when I was a teenager, I gradually came to the conclusion that the world was probably going to end sometime soon. And this had a lot to do with science fiction movies like The Terminator. Each one has a different explanation for how the world is likely to end or come to some major point of crisis. And there were so many of these that I kind of gradually came to assuming that it was probably going to happen. And then I got to college and I started thinking about it, and I was thinking like, actually, there's a fair chance maybe the world's not going to end, at least not anytime soon, and it's worth investing in the future. And started, it was sort of a coming of age thing. I started to think, the future was worth investing in. So given that history, it is a little surreal sometimes to look at present day headlines like this from serious sources. This is Wired magazine. And they say things like, the quantum apocalypse is coming. Be very afraid. What happens when quantum computers can finally crack encryption and break into the world's best kept secrets? It's called Q-Day, the worst holiday maybe ever. So to some extent, the apocalypse theme is still there whenever you look for it. So the goal behind this talk, what I wanted to do with this talk, is to actually get behind these headlines and try to figure out to what extent there's truth to this and what we can do about it. So the short answer, I'll go ahead and give away the punchline. The short answer is that we might have an apocalypse if we're not prepared. The good news is that people are preparing, and so the world's probably not going to fall apart, but we need to be ready for this thing. And so we do all that. They'll make a movie about what could have happened, and everybody's happy. This is what the overall structure of the talk looks like. I'm starting in the long past, and then I'm going to go up right to around the present day in terms of explaining what motivates this phrase, the quantum apocalypse, that some popular sources are using. And I've just chosen a few kind of key points to start with, and they both show this kind of building of the story. And one of the things we're going to discover about this is that a lot of what's happened here is just kind of accidental. There's a convergence of different lines of progress in science. I think it's fair to say that nobody expected this particular progression 100 years ago, but it's kind of what we're contending with, and it generates a lot of creative ideas. Okay, and there's two themes we're encountering through this kind of historical progression. One is what I'll call finding the smallest thing, which I think is a goal that motivates a lot of science. It's just we say, okay, we have this system, let's break it down into components and study each of the components so we can understand the whole. And then we take those components and we break them down even further into subcomponents and keep looking for the simplest, most elementary thing. And then the other theme in this talk is what I'll call really hard problems. And these are computational or mathematical problems that I think are very hard now, and that we expect or hope will continue to be really hard even into the future, even as computation and human thought advances. And what we see in cryptography is that really hard problems are actually useful to us. Really hard is good in some ways. Okay, so starting with the story way back at the beginning. I'm not a historian, so I'm not going to try to say exactly when, but in the BC years, there was Euclid's algorithm and an early mathematical discovery. And this is one reason this is a nice starting point is this is the one time in the talk when we're going to be able to set a goal and actually achieve it. A lot of the other stuff, a lot of the stories I'm going to tell are about setting a goal and finding that we don't achieve it or it takes us in a completely different direction. But in the case of Euclid's algorithm, we can set a goal and actually achieve it. Euclid's algorithm, I looked it up. We have this original text version, and then we have the translation. The translation, I have to say, even being a mathematician, I find is impossible to read. And I think it's actually better to not only state, but also explain the algorithm using no words at all. So this is my attempt to explain the algorithm without words. Okay, so that's Euclid's algorithm. So basically what we're doing here is we're taking two numbers and we're trying to find a smaller number that evenly divides both of them. So greatest common factor. And the nice thing about this is what we would consider an efficient algorithm in the sense that even if we started with substantially large numbers, like, even if they were 10 digits long, with a calculator or whatever, we could carry this out in a reasonable amount of time because those numbers, they shrink pretty quickly. What we effectively did there is we took the two numbers that we started with and we started subtracting one off the other. So we take the smaller one, we subtract it into the lower one, we keep taking remainders and until we break it down into something that evenly divides both of the numbers that we have. And so that's our first example of finding the smallest thing. In this case, it's in an abstract setting, and we have an efficient and always reliable way of doing that. Okay, so that's Euclid's algorithm. So zooming way forward to 1927. So here we are continuing to talk about finding the smallest thing, but this is a case where it takes a very different turn, and the answer that we get is not nearly as definite as what we got for Euclid's algorithm. So I chose 1927 because it was sort of a flashpoint for quantum physics. It is when certain things were realized that were not merely physical, but also kind of philosophical. And we can begin to understand that if we look at this phenomenon of blurriness that'll happen when we're trying to search for the smallest thing or the smallest unit in a particular system. So I just chose a random painting here. We notice that if we take this painting and we just choose a point and we keep zooming in and keep zooming in, eventually we're getting to a point where we can't really seem to see much anymore. And we've kind of lost focus and we don't really know what we're looking at. And this effect, I think, when if I see this for the first time, my natural assumption would be to say, okay, well, this is probably a limitation of the medium that I'm looking at. So in this case, I've got this is a painting, so obviously there's limits to how finely the painter could draw, and also we're looking at a digital image, so we're also hitting limits there. This pixels are of a certain size. So a question that we can naturally ask is, if we encounter this kind of blurriness, is it always the result of just a limitation in the observation, the method of observation? And one of the key insights from the 20s was that it is actually not merely a limitation in observation, that it may actually reflect the way that reality is. And I'm going to present something from this historical figure, which captures this. It's another translation like the one from Euclid, but it's a little easier to follow. So what he said was, the fallacy of the law of causality, which is when we know the present precisely, we can predict the future, is not the conclusion, but the assumption. Even in principle, we cannot know the present in all detail. And that was Werner Heisenberg. So the key sentence is, even in principle, we cannot know the present in all detail. So it's hopeless to try to exactly model the universe and then just based on that predict everything that's going to happen in the future, because the goal of trying to get exactly the state of things at any given moment is hopeless. And the reason he believed that was because of this idea of superposition. the idea that a physical system can be in multiple states at the same time. And so in a sense, so if we're looking at this idea that, we're trying to find where an object is, and instead all we have is this blur, what Heisenberg says is actually this blur is reality. This is a wave function. It is something that is actually spread out in space. It can't be nailed down to one particular position and momentum at the same time. But with that comes some useful things, because even though these systems are described by these something in multiple states at the same time, they still obey precise mathematical rules. So once we accept the fact that we can't completely nail them down, we can then find the rules that govern their behavior when they're occupying these superposed states. And then that gets us into quantum logic and quantum physics. So we can start to talk about what these rules are, and I've described them here in kind of conceptual and visual and auditory ways, but of course there's also mathematical descriptions that go along with them. So starting with the very simplest type of system that is not purely classical, and that is a qubit, and that would be a quantum system which has two possible basic states, and that it may be simultaneously in both those states at once. And there's a nice conceptual model for this, which is called the block ball or the block sphere. So let's just arbitrarily label the two states that the qubit could be in. So an example of this would be, you can have a case where you have a photon that is simultaneously in two places at the same time. So one location we're going to call 0, and the other one we're going to call 1. Those are the basic states. So I'll draw points for the 0 and for the 1. And then we'll say, if the qubit were in one state or the other, but we simply didn't know which one it was in, then we will model that by a point that is exactly halfway in between the two basic state points. So that represents classical uncertainty, and that's not anything new. And then we say, okay, well, if the qubit is both simultaneously 0 and 1, then we have a whole range of possible states, and those states trace out an entire ball, where the original basic states are two antipodal points on the ball. So the states that are the most quantum are the ones that are on the surface of the ball. Those would be the pure states, and those are in pure superposition between the 0 and the 1. And then the ones that are in the interior but not in the center, those are the ones that are kind of classical but kind of quantum at the same time. They're kind of a mix of both uncertainty and also actual superposition. So we have that. And this is a really nice model, because actually, pretty much anything you want to do with just a single qubit, you can actually model it using the block sphere. So there's certain manipulations you can do of the state without destroying it. If you put it through like a single quantum gate, that corresponds to rotating the ball. And then measurement that can also be described in physical terms. If you want to take it and you want to say, okay, well, let's observe it and figure out where it is. Is it in 0 or is it in 1? You can figure out those rules geometrically. So that's the qubit. So that's the simplest one. And then if we want to move to higher states, we can also come up with nice descriptions for what the possible superpositions look like. Trying to continue with the model of the block sphere becomes difficult, because that would take us into higher dimensions that are harder to visualize. So it can be helpful, instead of using the block sphere, to instead use the wave function. It's mathematically the same, but it's just a little easier to see. So let's say instead of two basic states, we have 5, and I've colored them here. And then a wave function would be a representation of a quantum state existing among these 5 basic states. And what it is first of all a magnitude associated with each of the 5 states, and then also a direction. So the direction is just a one-dimensional parameter. We can think of it as just an angle. And so physically what this represents is, so the magnitude is, that tells us if we were to measure the state and actually figure out which basic state it's in, the probability that it would assign to any given basic state is determined by that magnitude. It's determined by that length squared. And then whereas the direction, which is also called the phase, that is something that is entirely quantum. That is something we never exactly see, but it is a necessary part of calculations that we do when we're dealing with these quantum systems. Okay, so that is what the quantum state looks like. We can also talk about what the quantum state sounds like. And I mean, so I think it's useful, first of all, since these things that we're talking about are a little hard to reach because they don't exist at the human scale. We really want to use all our senses to try to understand them. And also, the sound part is useful when we're dealing with wave functions that have lots and lots of basic states. So if we're getting to the point where there's so many basic states, it would be harder to keep track of, all the individual values of the wave function. It can be useful to look at it instead as a sound wave. And if we do that, then we can actually, in a sense, hear what it sounds like. So this is a sine wave, and I'm just going to play it as a sound, just like that. Okay, so that's simply a tone. So that's a single tone. I think it might be 100 hertz or something. And when the quantum wave has this nice shape, that is what we're going to hear. And then if I take another one and if I speed it up, this is half the wavelength of the previous one. Then we get the same tone, except it's one octave higher. And the nice thing is about this that we as humans we're pretty good at hearing simultaneous tones at the same time. So for example, this is both of those sounds at the same time. And so that allows us to pick out what is going on without necessarily having to map out the entire waveform. And the nice thing is, in a sense, this way of understanding things in terms of tones is completely universal because Fourier analysis tells us that if we take any repeating waveform, even if it's ridiculously complicated, as long as it has a period, as long as it repeats itself every certain wavelength, then you can always break it down into tones. There will always be a certain base frequency, and then there'll be overtone frequencies like that octave we were looking at, or even higher frequencies. And so in a sense, you can always express it as like a chord in music, even if it's kind of a discordant sound. So this one, I think, was a result of putting together 4 different waveforms on top of each other. Okay, and the great thing is this isn't merely a conceptual aid. It does actually represent something that in theory we could do with a quantum computer if we had one. And that is what they call the quantum Fourier transform, which is one of the earliest discoveries in quantum computing back in the 80s. And basically what they found was if you have a quantum state that is in one of these periodic forms, so its wave function actually is represented by this function that repeats itself according to a certain wavelength, then there is an efficient procedure that you could apply to that waveform that would tell you one of the frequencies at random. So in this case, I created this by throwing together a bunch of different waveforms at a bunch of different frequencies. One of them was 500 hertz. And so if we were to run this through the quantum Fourier transform, it would randomly tell us one of those frequencies. And in this case, I think since there's only 4 frequencies, if we ran it a few times, we would basically have a complete map of the entire function, because it would eventually tell us all 4, and it would be like, okay, then we know exactly the spectrum of this waveform, we know exactly what it is. And the nice thing is that is so much more efficient than the alternative. The alternative would have been to just take the waveform, many copies of it, and just measure it over and over again. And each time we do, we'd get a single point on the function. And we'd have to do that so many times before we'd actually get a realistic picture of what it looked like. So the quantum Fourier transform in some settings is much better than that. It's much more efficient. Okay. Okay, so just summing that up, so this was so the idea of quantum superposition arising in the 1920s, and then since then, all our different ways of trying to understand it, understand this thing that happens at microscopic scales. We can't actually see directly, but we can understand through indirect means. Okay, next date that I wanted to talk about was 1950. And this is less of a historical flashpoint, but more of just kind of an academic oddity that happens to be relevant to us. And this is where we start to get into the theme of really hard problems. So if we're talking about problems that, so in 1950, digital computing was still in its very early stages. People projected and guessed that certain computational problems were hard. And as we're going to see, some of them are still hard today. So sometimes when we declare something to be hard, it does turn out that decades later it's still hard. And in a way that's encouraging because we need that for cryptography. So the specific problem that I had in mind was the chess problem. And that is, if we're given a particular chess position, we want to determine whether it's a winning position for white, a winning position for black, or a draw. So what we're assuming here is, hypothetically, if we had players that were so good that they always played optimally on both sides, the question is, who would win? Would it be white or would it be black, or would it be a draw? And we know, based on the way that chess is constructed, that this is a question that always does have an answer, because chess is a finite game. It's designed in such a way that it can't go on forever. So we know at the end of the day, somebody's going to win or there's going to be a draw. But the question of whether evaluating this for a given board position is incredibly hard. And this was considered by Claude Shannon, who was one of the founders of information theory, did tons of major work that is still relevant today. He happened to write a paper called Programming a Computer for Playing Chess. So again, bearing in mind, this is way long ago, before computers could do very much with much speed. And he estimated that there are on the order of 10 to the 43 possible board positions and at least 10 to the 120 possible games. And this is a way of quantifying hardness. When it's 10 to the 43, we can say this is definitely hard, and it was hard back then. It's still hard today. 10 to the 20 we can handle. 10 to the 40, 10 to the 50, that's still out of reach for today's computers. And this is one reason why today we still don't have perfect chess computers. We have very good ones, but we don't have anyone that can guarantee to get it right every time. Okay. So chess is an example of a really hard problem, but I will qualify that by saying that sometimes there is what you would call a trapdoor. And this is true in general of these really hard problems. Sometimes if they are designed in such a way that they appear really hard, but with a little bit of information, you can actually get the answer much more quickly than it might appear that you could. And for an example of one of these, I brought up something from a book of chess problems. So this is a case where you have, enough pieces on the board that there are many possible moves. It would probably be very difficult to map out every single thing that white and black could do in the future. So on the face, we don't necessarily know if white's going to win or black is going to win. What we have here is a position where white is the one who's going to move, and so by that metric, they might appear to have an advantage. However, black is threatening to do two things at once. One thing, it's threatening to checkmate by moving the queen onto the king's rank. And on the other hand, it's also threatening to take the knight. So whatever white does, it's going to have to, in some sense, deal with those threats. So the question is, and we could pose this to a computer if we wanted to. The question is this a winning position for white, for black, or does it lead to a draw? And the answer turns out to be it is a winning position for white, and this is why. So if the queen does something that maybe seems unexpected, which is to move directly next to the king and basically sacrifice the queen, which is a non-obvious move, then there's only one move for black, and that is to take the queen. Anything you could take with the king, but that would be moving into check. So the queen gets captured, the rook moves over. And then at this point, the knight does not take the rook, it instead takes the bishop. And now the king is in check, so again, there's only one possible move, and that is to take the knight. And then at this point, it is actually mate in one. And because of this elaborate setup, the king is now trapped, and the column that it is on is now open. White can move the rook over to the king's column and checkmate. Okay. So, and that happened to have an easy answer, and that was because it was arranged to have an easy answer. And the point of all that is we bypassed having to map out the entire tree of possibilities for black and for white. And we were able to do that because there was a trick. With a little bit of information, we could tell somebody that, and they could check it, and they'd be like, okay, yeah, you're right. Yeah, this is a winning position for white. You know the answer. Okay, so that's trapdoors. Moving ahead to 1977. And this is when, so we're continuing with this theme of really hard problems. And this is when we start to see examples of putting these really hard problems to use to do something practical. And then the basic question that kind of motivates this segment is whether we could take one of these really hard problems and use them to encrypt information. Can we take a message and hide it in a puzzle in such a way that somebody recovering it without authorization, it would be really hard. So in principle, if the information is there, then it's always the case that some all-powerful computer could fish it out, just as an all-powerful computer could tell us whether a particular chess game is a winning position for white or for black. But if we're willing to say, okay, we believe that this class of problems is still really hard, even for the best supercomputers, then we might still have reliable information security. And that is what we're going for. So assuming hypothetically we have two parties that wish to communicate, who we're going to call Alice and Bob. Bob has a message, which we're going to assume is just a string of bits. And he wants to send it over to Alice, and he wants to do it in such a way that nobody except Alice can read it. So he creates a puzzle. He designs it specifically for that message. And that is the encryption. And then he sends it over to Alice. And then we're going to arrange it in such a way that Alice and only Alice has some sort of trapdoor that allows her to decrypt the message, but nobody else could. And we want some sort of reliable guarantee of security in that case. And the key thing is, so this idea, the idea of encryption has been around for forever. But the thing that was realized in the 70s was this idea that we want to make it possible for people to encrypt without being able to decrypt. So we said only Alice should be able to read messages that are intended for her. That even means that if somebody else were to send a message to Alice, Bob should not be able to read it. He should only be able to encrypt and not be able to decrypt. And that is what we're calling public key cryptography. It's public because the information that Bob used to do the encryption was public, but that itself should not be enough to actually encrypt. And the mere fact that this is possible is actually pretty amazing. What we're actually saying is Alice and Bob, they could have never, it's possible they never met in the past. They've exchanged no information, no secret information. They're communicating across the globe. And nonetheless, they are actually able to set up through a public channel this kind of communication that allows only Alice to decrypt information sent by Bob. So the question is, how can we actually do that? And the original design that came up in the late 70s was one that was based on just simple arithmetic, basically just calculator arithmetic. And I've put together an example here. In reality, the numbers that we're going to be using here are smaller than you would use for an actual transmission, but they're not that much smaller. In reality, we'd be using like 100 digits instead of like 8 digits. But the same basic idea that we're using here can be used to actually encrypt real information. So I'm going to represent Bob's message as a number. In this case, I just arbitrarily chose 19. And then we're going to have another number, which I'm calling the encoder. And this is basically, this is particular to Alice. She is using this number for her own transmission. So she at some point would have broadcast this number, say, hey, if you want to send me messages, please use this number to do it. And then, so we're going to take these two numbers together, and we're basically going to do a few calculator tricks with them and see what happens. So I'm going to put just, for now, just two extra buttons on this calculator. One is multiplying by m, and the other is modding out by r. So we can multiply by m, or we can do integer division by r and just take the remainder. And by repeatedly using these buttons, we can get some equations involving m. So first of all, m to the 1 equals 19. That's obvious. If I multiply by m again, m squared, 361. Do that a few times, and then eventually, when it gets big enough, I'll mod out by r. Modding out by r helps us keep everything to a reasonable size, so that we don't go off the display of the calculator. And then I can keep doing that, and then to speed things up, I'm going to introduce an x squared button. This is the same as just multiplying by m over and over again, but it's going to make it go faster. So rather than multiplying by m again, I'll square it. I get m to the 10th equals that. So it keeps either squaring or multiplying by m, and every time we're modding out by r. Keep doing that. And I'm just going to do this a bunch of times until I get a reasonably large exponent. Okay. So the point of all that was just to show that getting equations that are of this form is actually not too difficult. You can do it on a calculator, you can do it on a computer very quickly. If you choose what the exponent is, a computer will very easily tell you the corresponding value, mod r. So that can be done fast. And then the result is we get some equation where we're going to assume that that an exterior party knows r but does not know m. So basically, we're looking at that equation, and this is what we'll call an RSA encryption of the message M. And we said that it was very easy to generate these equations, but to reverse the process might be potentially quite a bit harder. There's no clear way to do that. The squaring and the multiplying, all that stuff, that's easy to carry out, not so easy to reverse on R. And that's why originally, at least, this was considered to be a strong form of encryption. So literally, we could imagine that when Bob is sending his encrypted message to Alice, what he says is, okay, Alice, I've got a message M, and it satisfies this equation, mod R. So that's all the information I'm going to give you. And then Alice, with her trapdoor, attempts to recover M from that information. So that's the form of the encoding of the message. And the security of all of that relies on this assumption. It relies on the assumption that these exponential equations, mod R, are really hard to solve if you don't have any additional information, if you don't have the trapdoor. And this is this easy to state assumption. So much has written on this assumption. So RSA encryption has used all over the globe, billions of dollars a day, transmitting securely through public key encryption. The security of all of that depends on the assumption that this is really hard. And so this, 1977 was the invention of this, but it developed, and it was used for decades to encode information. So it brings us forward to 1994, following all this public key development, the theoretical and the actual implementation of public key cryptography. Where the assumption about those exponential equations, mod R, was kind of called into question. And it was particularly because of the convergence of that with the development of the idea of quantum computing and the idea of quantum technology. So there was, plenty of study of the problem of solving those exponential equations with classical algorithms. And as of today, the most efficient algorithms to break those equations are still pretty inefficient. But somebody else had the idea that we could theoretically try to break these same equations using a quantum computer instead. And that person was Peter Shor, a mathematician. And what he literally studied was a very similar equation to the one we were just looking at. It's slightly different. And it is the question of whether given x and given r, we could find the smallest positive value of p such that x to the p equals 1 mod r. So it's not exactly the same as the RSA equation, but it turns out if you can solve this one, you can actually solve the RSA equation. It's just as good. And what he did was he figured out a way in theory to use the unique quantum properties to break this equation. And what we can imagine is we have, again, a calculator, but we're going to assume that it's a little different from the one that we were using before, because when we give it an input, we are actually permitted to give it a superposition of possible inputs. We don't have to actually give it a specific number. We are actually permitted to give it a superposition of numbers and then see what happens. So let's suppose we have our x, which was given as part of the statement of the problem. And then, so calculators have the ability to exponentiate mod r. We know how to do that. But let's say that I don't give it a specific exponent. I instead give it a superposition of possible exponents, which we're going to represent like that. So we can imagine this is the exponent is in itself a wave function, and it's a completely uniform wave function. It has the same magnitude and the same direction applied to every possible input up to a certain value. It's finite, but yeah. So we just choose a maximum value and we give a superposition of all inputs up to that value. So the question is, what happens if we take this and we're plugging it into a quantum calculator, which is, think of it as it's an idealized version of a quantum computer. What these devices would have, in theory, is the ability to manipulate and do arithmetic operations on these superposed states. So it wouldn't measure yet. It wouldn't measure the actual state. What it would do is it would, in a sense, simultaneously carry out certain arithmetic operations on this exponent without knowing what it is. So if we take x to this wave function, then we get a superposition of possible outcomes mod r. So we're going to get, at this point, so we have simultaneously a superposition both over the exponent and the outcome of the exponentiation. And then we could take that and measure it. And the result of measuring is that we get a definite outcome for the value of the exponentiation. And that causes a collapse. The result is we don't necessarily find out what the exponent is because there could be multiple possible exponents that would give the same value. What it effectively does is the exponent collapses into a superposition of all the possible exponents that would have given us this number, 331904. And so what does that look like? So if we take x and we exponentiate it many times, it forms a regular pattern. And the period of that sequence is exactly p. It's exactly the number that we're looking for. So that means what we have at this point is we have some superposition of possible numbers, and they're all separated exactly by that value p. And then the question is, what are we going to do with that? A natural thing to do would be to simply measure it and then find out what the value is. But then all we'd get is an expression of the form x is something equals something, and that's useless. We could have done that with a regular calculator. That's boring. So instead what we do is we plug it into the quantum Fourier transform, and this is when we get to start doing uniquely quantum stuff. The quantum Fourier transform takes that, and it gives us not necessarily p, but it gives us approximately a multiple of p. So this kind of spike waveform that we have here is you can think of it as an addition of several waveforms, and all of them have period p. So you would have the sine wave with period p, and then you might have some component of the sine wave with period p over 2 and p over 3, p over 4, and so forth. It's going to give us some sort of overtone frequency. And then what do we do at this point? We've lost the wave function, but fortunately we can just create a new one, possibly translate it, and then repeat the same procedure. And then the result is that we get another approximate multiple of p, and then repeat again, and get a third one. And then once we have enough of those, there is a simple procedure that we know, which will carry out the final step, which is Euclid's algorithm. Euclid's algorithm has that ability to give us the least common multiple of a set of numbers. And in this case, even if it's a little bit off, even if it's a little, if it's only approximate, Euclid's algorithm will still work. And it gives us exactly the number p. So all these components taken together actually allow us to recover p. And the key thing to observe is that if, in theory, if we had a fully functioning quantum computer, the number of steps here to carry all this out is not actually that many. So quantum Fourier transformation, that is an efficient algorithm. And overall, the number of steps that we'd have to take is merely polynomial in the number of digits of the numbers that we started with, the number of digits of x and r. And so it's it's not, as far as computer science is concerned, it's actually not that big. And it is definitely not what we consider really hard. In fact, we would consider quite the opposite. A quantum computer makes this problem easy. So this whole assumption on which billions of dollars are riding is false. Okay, so if we can imagine that this was 1994 and this had just been discovered, and we're at a point in history where nothing remotely approaching a quantum computer actually exists. And yet at the same time, we know in theory that these things could happen someday. And so there's this kind of limbo state. And meanwhile, quantum computing starts to advance, we have Nielsen and Schwang, which is one of the first major textbooks on the subject. And we have, so academically, the discipline advances more and more. We have conferences and that kind of thing. And also at the same time, people are starting to build prototype quantum computers. And they start to make claims like, we can factor the number 15 or some small number like that. And there's a lot of debate about, how seriously do we take this? And then we had a Nobel Prize in Physics in 2012, which was quite significant. There are a lot of previous Nobel Prizes that were relevant to quantum computing. That one was quite directly addressing quantum computing. And then that brings us all the way up to 2015. And this is when things started to become less academic and a lot more tangible. So 2016, a number of things happened kind of simultaneously and not coincidentally. So one was, this was right around the time when there was a huge influx of investments into quantum computing. And there was a big spike in money and resources going into the possibility of building a quantum computer. And then along with that, certain authorities, including NIST, pointed out that we really need to start taking Shor's algorithm seriously from the perspective of cryptography. So they wrote this, and this was just before I got there. It said, in the 20 years since Shor's discovery, the theory of quantum algorithms has developed significantly. We must begin now to prepare our information security systems to be able to resist quantum computing. So actually saying specifically, this is no longer going to be considered an eventual threat. We are going to treat it as something we need to deal with right now. And then a couple of years later, the National Academy of Sciences, Engineering, and Medicine wrote a much longer report where they said something that was a lot more strongly worded. They said the invention of a scalable general-purpose quantum computer would constitute a total, simultaneous, instantaneous, worldwide compromise of all of today's public key cryptographic algorithms. So general, alerting the public that this is something that we needed to deal with and without delay. So then NIST in 2016 started the Post-Quantum Cryptography Project. So NIST is responsible for standardizing protocols for all the non-intelligence federal government information systems in the country. And then by extension, a lot of our standards are used by industry as well. And so as part of that, NIST started this Post-Quantum Cryptography Project. And the goal, and as we've done before, we invite the international community to submit possible candidates for cryptography, and then there's a public evaluation period during which we consider them and weigh out the relative merits. And the goal was that we wanted to find new assumptions on which to base these post-quantum cryptographic protocols. So the idea is we don't want to get fooled again. We had a previous assumption that turned out not to be true. And it happened that this exponentiation assumption was particularly vulnerable to quantum computers. So we want to redesign everything from the ground up, and we want to base them on computational assumptions. And we want these to be assumptions that are both hard to break now, and also we expect hard to break decades into the future. And so the question is, where do we find these assumptions? And one thing that I think, continues to always be true in cryptography is that the simpler we can state these assumptions, the better, because it's easiest to see the assumptions from all angles and really say that we've tried everything we can think of to attack it if it's a simply stated problem. And it turns out that for constructing these, we can actually go back to chess. Chess actually makes a very good model for coming up with new, difficult problems to solve. So I could ask the question, how quickly does a chess piece move? If I give you the rules for how it moves and I tell you a square I want to move it to, can you tell me how quickly it'll get there? And in the original chessboard situation, this is not too hard to answer. You can just exhaustively search. I've drawn a grid of how quickly a knight can move on a single 8x8 chessboard. That's pretty easy to answer. But if I were to give you a knight on a bigger chessboard, higher dimensions and larger, and I was an arbitrary knight, I could actually choose, what the moves were. I can say, you are allowed to move this many squares up and simultaneously this many squares over, and I describe for each dimension, what the move is. And if I give you all those things, and then I ask what would be the least number of moves you would need to get this super knight to some square that is very close to, but not at the square that it started with, and what would it take to do that? And it turns out, as far as we know, with all the best available methods, this is a very hard problem to answer with both quantum computers and classical computers. So using numbers that might be large for humans, but not that large for computers, like 512 and 12,289, it is believed that answering that question is really, really hard. And even the best supercomputers today would not be able to do it. And it is that type of assumption that is the basis for what we call lattice-based cryptography. So lattice refers to kind of the set of possible moves that could be reached by such a piece. And so the idea is, so we're factoring out the door because we know that we're throwing modular explanation out the door because we know that's easy. And instead we're replacing it with these lattices and rebuilding everything using these lattice-based assumptions like the hardness of the moving of the knight. So 2016 was when all that started. And then we had an evaluation process lasting several years. And then in 2024, NIST selected 5 new post-quantum cryptographic algorithms to replace RSA. So the specific focus here is we are creating algorithms for 2 things. We're creating algorithms for public key encryption and also algorithms for public key authentication or digital signing, which are kind of the 2 original problems in cryptography. RSA had done both of those things. We need a complete replacement for RSA. And we chose 5 algorithms, all of which came from the international community. They were dilithium, Falcon, HQC, Kyber, and Sphinx Plus. 3 of the 5 were lattice-based, and I'm going to say a little more about this at the end and also talk about the other ones. So that chess approach was used in 3 of the 5. Dilithium, Falcon, and Sphinx Plus are all digital signing algorithms, and then HQC and Kyber are the encryption algorithms. And so together we have a package for doing both confidentiality and also authentication. And then current steps, which are currently underway, is implementation, which we're always encouraging the public needs to happen fast because, quantum computers are coming. And then also deepening the security analysis. So trying to find, at the end of the day, we want to be able to say, we are confident that if these simply stated computational assumptions are true, then these algorithms are secure. They can't be broken. And this is a page for the migration to post-quantum cryptography from the NIST Cybersecurity Center of Excellence. And this is for actually getting these algorithms out there and putting them into practice.
Carl, okay. Sorry, can I quickly interrupt and ask a small clarification question? So on the previous slide, you listed a bunch of algorithms for encryption and digital signatures, right? And you said that the security analysis is like one of the next steps. I was a bit confused because, okay, I should know this, I'm sorry. But I wasn't sure when you say that so these are basically based on hardness of some lattice problem already, right? So I thought that these algorithms would have some kind of a reduction to the lattice problem already. Yeah. Is that not the case? So how should I think about this?
Yeah, so in general they do. So I think what I'm talking about is like improvement of the security analysis. So for example, you might have a scheme where they proved that for a certain parameter range, there is an explicit reduction to the underlying security problem. But we would like to make that even better. We'd like to be able to prove that even with parameters are smaller, even if we're using a more efficient version of the algorithm, then we want to prove that security analysis still applies. So yeah, so it's true. We already have these good security proofs, but we want to make them even better.
I see. Thanks. And one more quick follow-up to that. So imagine a world where we are able to break lattices. Mm-hmm. We just classically, we don't have quantum computers, mm-hmm. And factoring is still hard. Mm-hmm. So having switched to post-quantum would have been deleterious, right, in that setting? Is that
Yeah, I mean, it's
really?
true if you switched fully to lattices, yeah, that would be in that universe, yeah.
I see. So is there a way that one can construct schemes that are sort of like, as long as either factoring remains hard or say lattices remains hard, as long as one of them is hard, the scheme remains secure? Are there such proposals as well that NIST cares about or have thought
Yeah,
about?
so yeah, I'm not that knowledgeable about it, but I've heard of hybrid. I think the word is hybrid for approaches that combine the pre-quantum and the post-quantum cryptography into one, and find assurance through both of those. So yeah, I think that is an area of interest.
I see. Okay, I'll ask you more later then. Thank you so much.
Okay. Any other questions at this point? Okay, so migration. So we're at the migration stage, moving things over and implementing these now standard cryptographic algorithms. And that pretty much brings us up to the present day. So there is one question that I haven't answered yet, which maybe nobody has answered yet, and that is, when are the quantum computers actually going to break RSA? So the short answer that I have to this is that this is a very hard thing to predict because there are so many human factors involved, and human factors are very hard to predict. I can say at least a little bit about the way I'm imagining it happening. So this is a kind of scientific flashpoint that will occur when experiment and theory meet one another. So the experimenters, they work on getting bigger and bigger systems over which we have more and more control, having more and more qubits and being able to manipulate them with more and more control. Meanwhile, the theoreticians work on ways of taking Shor's algorithm, for example, and making it as accessible as possible, lowering the threshold for the resources that we need in order to do it. So we have those two lines of progress, and it's when they come together that we'll have this scenario. So a couple examples of progress in both directions, and these are from a year or two ago. So there was a very interesting talk by Ben Reichart at one of the QIP conferences about a system using 256 qubits with a good ability to manipulate those qubits. And then there was last year a paper by Craig Gidney where he was lowering the threshold for the number of qubits that you would need in order to break RSA. So on the one hand, you got 256, and on the other hand, you got 1,000,000. Now, this slide actually was prepared last year because I gave this talk once before last year. Since then, stuff has happened. And I'm just going to give an example to show how quickly everything is moving. There is this paper from the archive from a few months ago where they said Shor's algorithm is possible with as few as 10,000 reconfigurable atomic qubits. So, and I put this up here just to emphasize things are moving very quickly. I'm still not going to try to, take a guess as to when this event is going to happen, but we can see that there's, things move fast. Okay. Yeah. So last thing I wanted to say before I dive into the technical part was just that this is a really fascinating field to work in, and one is that we have kind of all these integrations of all these different schools of thought all coming together, and it's a lot of fun to see, and it's highly unpredictable direction. Okay, so I wanted to finish by going a little bit into the technical parts of this because I was told there were some researchers in the audience, and say a little more about these new classes of really hard problems, the one that underlie post-quantum cryptography. And as always, we're aiming to understand these problems as best we can and try to the extent we're capable, to measure just how hard they really are, because we want them to be reliably hard for a long time to come. So lattice problems were the ones that I already mentioned, and we can think of them in terms of chessboards, or we can think of them in terms of modular arithmetic. I'll identify three basic versions of lattice problems that are used as a basis for cryptography. So one is the shortest vector problem, which is maybe the simplest one of all. Shortest vector problem would be, given a set of linearly independent vectors in R to the n, find the shortest non-zero vector that can be expressed as integer linear combinations of those vectors. So this could be a case where the vectors themselves are very large, but there's some hidden integer linear combination that is quite small. And the question is, can you find it? And that's believed to be computationally very difficult. Another similar one, which is more directly adaptable to cryptography, is the shortest integer solution problem. And this is when we start working in a modulus ring, Z mod Q, for some positive integer Q. And the question is, given a random matrix A over Z mod QZ, find the shortest non-zero vector in the null space of that matrix. And so, solving and solving an equation like this is just linear algebra. That's easy. But once we show in the question of length, it becomes a lot more difficult. And finding the shortest non-zero vector is believed to be a very hard problem. And then there's learning with errors, which is a little harder, a little more complicated to state, but a very versatile question. And this is basically what are called noisy linear algebra. So if we were given a random matrix A, and then we're given a vector of V, which we know to be of the form AX plus E, where X is uniformly randomly chosen, and E is a Gaussian vector, meaning its entries are chosen according to a Gaussian distribution around 0. Then the question is, can we recover X from that? And this is the thing that would be easy to do if we didn't have that noise vector E. If it was just V equals AX, then it would be simply linear algebra over ZQ. Very efficient, very fast. But our belief is that when we add in these additional terms, E1, E2, E3, even though they're quite small, suddenly the problem becomes a lot harder. And a form of the LWA assumption actually assumes that you could not get any information at all about X from V and from A. So not only could you not recover it, but you wouldn't know anything at all about it. So it's a very useful assumption. And as I mentioned before, so 3 of the NIST standard schemes are based on lattice assumptions like these, and those are Kyber and dilithium and Falcon. Another family of really hard problems from the post-quantum cryptography.
Sorry, Carl. Can I interrupt? Just a quick clarification. So, do we know any relations between the previous set of lattice problems that you mentioned? Is it known which one is, or are they incomparable somehow?
So I think they're proved. So I think shortest vector problem is sort of the original one. That's kind of the touchstone. And I think there are proofs, at least for some parameter ranges, that will show that shortest integer solution and LWE are at least as hard as shortest vector problem. So yeah, I think there are reductions that relate them to one another.
So ideally, one would want to use the shortest vector because that seems to be the weakest from what we know. Is it?
I mean, the way that I think of it is, so the shortest vector is nice because it's so easy to state. It's just it's such a natural, simple problem. So I think when people find those proofs that tie everything back to shortest vector, I think that's the motivation, the idea that we can, in some sense, show that the hardness of a given algorithm is based on this very simple original problem, which is the shortest vector problem.
Thank you.
Okay, and then another family of problems we can use are the code problems. So here we're dealing with usually binary codes. So these are, so instead of dealing with Z mod Q, we're instead dealing with Z mod 2. And an example of a code problem would be the syndrome decoding problem. So given a random matrix A over Z mod 2, find the non-zero vector X in the null space of A that has the least number of ones. So it looks pretty similar to the shortest integer solution. We're just measuring size in a different way. We're measuring it using Hamming weight, which is the number of ones in the code word. And so again, this is a problem that is easy to state, but as far as we know, is difficult to solve. And this goes way back because Shannon, early in the days of coding theory, proved that random codes are actually optimal in a sense for transmitting message through a noisy channel, but that this result isn't directly useful because, as far as we know, it's not directly useful because we don't know how to decode random codes, and that's essentially what this is asserting. Decoding these random codes is very hard. So HQC is an example of a scheme that is based on that. And then there is hash problems, which are of a very different form, but they have a long history and are also very solid. So a hash function is basically it's a function from a set to a set of bit strings of some fixed length. And that, the outcome of the function is called the hash. And roughly speaking, it is a function that is designed to efficiently mix up its inputs as much as possible. And when we look at the descriptions of these algorithms, there's just lots of different mixing operations, and we kind of imply them in sequence. And this is SHA-3, which is a standard NIST hash function. And it's a diagram of one of the operations used to mix it up. And the idea is, so if we've taken one of these hash functions and it's sufficiently mixing, then we assume that certain problems are difficult. One of them is pre-image resistance, and that is given y in the range of h, try to find x such that h of x equals y. And then another is second pre-image resistance, given z, find x such that h of x equals h of z. So hash functions get used all over the place. They're used in all of the previous protocols that I mentioned. So in addition to code-based and lattice-based assumptions, they also use hash-based assumptions. And then we have at least one important algorithm that is based only on these hash assumptions, and that is Sphinx Plus. So similarly, these assumptions about the hardness of recovering certain solutions from a hash function can also form the basis for public key cryptography. So the good news is all these problems have a long academic history. They're all well studied. And you can see, for example, there are like lattice challenges online where problems have been posed to the public about solving lattice instances of those lattice problems at certain parameter ranges. And that there's a map there that can give us a sense of how far current computing technology is. And we will only use parameters that are safely out of the range of any possible attacks. And while there are somewhat faster quantum algorithms for these problems, they are not significant enough to be considered a threat. So in the case of Shor's algorithm, you have a huge improvement offered by Shor's algorithm over the best known classical algorithms. Whereas in the case of these problems, it's much more modest and it does not threaten current algorithms. So the result is the future looks a lot more secure once we've implemented post-quantum cryptography. And that brings me to the end, and I'm happy to answer any questions.